Okay, it's already 11:49. By the way, can you hear me?
Yes, so we can hear you.
Doctor.
Yes.
All right. Okay, as promised, Wang, can you share your answer? Um, put it in WhatsApp group also can. I will try to display it over here. Okay, thank you, Wang. Try to download it first. Okay, this is what we have from Wang. This is his answer. Okay. Oh, this is question number 2. Wang, is question number 2 at the bottom here? Oh, okay. We put extra, but we discuss on this one first, yeah? All right. Thank you so much, Wang, for your sharing. And now we try to compare our answer. Right. Okay. This is what I have for the solution. And in general, before we get into the solution, we have a look at the question first. In general, the question here, we have to build a Thevenin equivalent circuit, and the allocated for this question is normally around 10 marks. And if I'm not mistaken, it was from previous tests, or I don't know, maybe test or final. I didn't remember about that. But this is a typical question you will, not the exact question, but this is what you might expect in your assessment. All right. Okay. Before that one, let me read through the question. Construct Thevenin equivalent circuit depicted in figure 1 at terminal A and B. This is the terminal, so we need to get a Thevenin equivalent circuit with respect to this terminal. Show all calculation to find elements of Thevenin equivalent circuit means that we need to show the calculation of finding the ZTH as well as VTH in this case. Okay, and according to the answer given by Wang, the first one, okay, he convert from time, the voltage over here, he convert from time domain into a frequency domain or phasor domain. And I'm not sure why this is negative 30. Maybe he tried to convert it into cosine, I think, maybe. Is it conversion to cosine? But basically, you don't need to do that. It just because you didn't mention about the cosine over here, so I assume that this is a direct conversion from time domain into a frequency domain. So in what do you call it? In general, this is correct, also correct, but you don't need to waste your time converting from sine to cosine unless it's stated that you need to present your answer in a cosine waveform. Okay, if you look at my solution, I just take the information using the sine equation over here, sine sinusoidal. So 160, the angle, I just put it over here. Why? Because maybe our answer later on may be slightly different because of this factor. But it's okay. The message over here, you try to convert from sine to cosine. But in maybe next time, you should write down the cosine waveform, the cosine equation over here, so that this negative 30 is really, I can get your the message very clear. Anyway, we proceed with, if you would like to solve this one, and looking at the question, all the elements, I mean, the components inside the circuit is given in its original value. For example, inductor in Henry and capacitor in microhenry, so that you need to convert into its phasor domain or frequency domain value, so that the value over here, all the components values should be in the unit of ohm. So here, the conversion, we use omega, take the information of omega in order for us to convert from its original value into ohm's value, and this is correct. So here, if you look, although Wang didn't mention about what is the value of omega, but I can get the information over here. So here is the information of omega, which is 200. And if you look my solution, I clearly stated that omega is 200. So here you will get marks lah, basically. And although it's not, we can always find the value of omega in your solution, but I think it's a good idea. It's a good idea that you inform your examiner more clearly. All right. In terms of calculation, I think both are correct. It should be 10, and this should be more J10. This should be negative J10. And according to my solution, I just calculate the value of XL and XC, not putting the J element. But if you do it like this, then it's okay. These two should also give you 2 marks. So now Wang have already collected 3 marks. And for ZTH, I get into ZTH. ZTH should be 10 minus J10. What we have over here is 10. All right, this is because of the the way you analyze the connection is wrong. If you look at the connection itself, yes, of course, it is in series. So Z1 over here, I put Z1 as R plus JXL because this is our Z1, and Z2 is the capacitor that we look over here. And these two elements, if this is considered as short circuit, oh, before that, Um, we need to set all sources into 0. Yeah. Since we have, in order for us to calculate ZTH, we need to we need to make all sources equal to 0. In this question, we have a voltage source over here, means that the voltage source should be treated as short circuit. And Wang also did that. And if he draw a circuit, with this circuit, I really would consider another mark, although the solution is wrong over here. But this is some kind of this one is some kind of extra mark to Wang, because he tried to inform me that this is the circuit we are looking at, and this element is a short circuit connection. Then this should be like consolation, extra mark lah, for Wang. Although the solution over here, I believe is wrong because of Wang wrongly analyze the connection of the elements in the circuit. Anyway, Wang, the elements should be the calculation should be based on parallel connected calculation, because we see over here Z1 and Z2 is connected in parallel, not in series. So Z1 should be coming from R plus JXL, because we have these two, resistor and inductor over here in series. So just add these two together. And this is the other element, Z2, which is, by right, it is in parallel connected with Z1. And towards the end, your answer should be 10 minus J10. All right, we're done with our ZTH, and later on we try to calculate ZTH. Sorry, not ZTH, VTH. All right, finding the VTH, of course, here I believe it is wrong lah, because of your ZTH already wrong over here, means that the rest of the calculation should be incorrect. And the strategy that you use over here, you use Kirchhoff voltage law, mesh over here, right? So negative V plus Z1 I, and Z1 is, but Z1 is, okay, now I get it. Now, okay, although ZTH is wrong, but here, Wang is entitled for another 1 mark, because half marks over here for Z1, another half mark over here for negative J10. So these two, 1 mark, half mark should be, I can consider give Wang this half and half, 1 mark, in total 1 mark. Take that, this also will give Wang another mark, although the ZTH is wrong, because we just put a series connected impedance over here. And as I said earlier, this connection, this calculation, sorry, not connection, calculation is wrong, because I don't see any circuit involving voltage over here. I don't know where did the student refer, but I can tell that the student would refer based on the original question, and based on the original question, he or she applied the Kirchhoff voltage law over here. And since since the current over here is wrong, okay, means that all the values over here is wrong, but the attempt to do it, to determine the VTH also, the method that you should use here is that you should have an equation like this. If you try to use Kirchhoff voltage law, Kirchhoff voltage law mesh analysis. you should have over here negative V, okay, plus I times Z1, okay, plus VTH, because actually VTH is the same as the voltage we look over here. So should have negative, this is negative V, going around this loop, this is negative V, this is another voltage drop over here, okay, consider that voltage drop, and the current, okay, the current here is basically I total. And okay, this is interesting because I total and the current that Wang give me over here is, I think, is the correct one, because I total is coming from this value V divided by Z1 plus Z2. Why we said that? Oh, this is interesting. Sharing section is very interesting. All right. Why? Because since this is open circuit, means that this one is open circuit, means that there is no current flowing through here. I over here is 0. So the rest of the current will flow into this loop, flowing through Z1, Z2, and get back into the source current. So what Wang calculate over here is what is the same as what available in my solution, I mean in the annotated version over here. I total equals to V divided by Z1 plus Z2. So Z1 plus Z2 is the total impedance, and if we would like to calculate the current, so we will use the total impedance over here. And I think up until this point, so negative V plus Z1 times ITH is correct, plus VTH is also correct, but over here we have problem, plus Z2 ITH, this is wrong basically. So in general, the answer that you gave over here is wrong. And of course, if this is wrong, this is also wrong. And what I can give you as consolation marks is that I would maybe consider half mark over here, because your effort to write down the equation, which is in general is wrong, but we have the pattern of what you're trying to do. So next time, make sure you redraw your circuit and try to give as much information to the examiner so that he can understand what's going on, or what you're trying to give in your solution. Otherwise, if maybe if I miss that point, the point over here, I would say that, okay, this is wrong, so definitely don't have marks. So now I have more time to comment, I mean to check your answer, then that I can find some of the strategy that you use here is correct. So you should get the marks from that. Okay, anyway, that is from one solution, and in total I would say this is 1, 2, 3, this is wrong, maybe 3.5, 4 over here, 4.5. 4.5 out of 10. So in total, we should have 10 marks for a complete solution. Okay, let's go into my solution. And anyway, thank you so much, Wang, for your effort. Okay, we're done with ZTH. Now we are focusing on VTH. Maybe I should erase this one first. In order for us to get the value of VTH, I would really recommend you guys to redraw the circuit via to give the examiner more information in your solution. So according to the circuit, we have a voltage. We put back the voltage over here, and we combine resistor and inductor and denote it as Z1. And this is the capacitor, and this is the voltage we are looking at, the VTH. And based on this kind of circuit arrangement, we know that we can simply apply a voltage divider rule in order for us to get what is the voltage of VTH, the value of VTH. So here, I apply voltage divider rule. And voltage divider rule says, if I would like to get the voltage value over here across Z2, so the equation should be Z2 divided by Z1 plus Z2 times the voltage from the source. And here is my answer, which is 160 with the angle of negative 30 volts. And apart from using voltage divider rule, you can also use a simple Ohm's law, where if you know what is the current flowing through here, I, let's say I label it as I. So if I would like to have what is the value of VTH, basically VTH is also equals to V across Z2 and can be calculated using I times Z2. And the way you calculate VTH here is that you try to apply a simple Ohm's law where you need to find what is the value of I over here, current flowing through Z. And in order to calculate, and in order to know what is the current over here, you need to refer back to your circuit, where you consider this one as open circuit. This is open circuit. And again, if this is open circuit, means that the current over here, I, is equals to 0. That, okay, there is no current flowing through this part. And I is basically the current that you've seen over here, the same current flowing through this element. So because there's no current flowing through here. And to get the value of I should be calculated using V divided by Z1 plus Z2. Okay, V over here. And since you got the current and multiply it with the value of your impedance, you can easily got your VTH. The difficult part here is that you need to know that this current should be 0 and this VTH is actually equals to voltage drop across this Z2 element or this impedance. And you should get the same answer as me. All right, towards the end, to really answer all the question inside question number 1, you need to construct the Thevenin equivalent circuit, and this is actually a free mark for you guys. I need to tell me that VTH and ZTH should be connected in series. Just by drawing these series connected elements and put back all the values that you calculated earlier, you can easily get another 2 marks. to complete your solution. So please, my advice is that please try to give as much information to the examiner in your solution, so that you can, although it is the answer is wrong, but the examiner or evaluator try to think about how can the examiner give you marks. I mean, in terms of effort and something like that. So try to give as much as possible information in your solution. All right, that's all for question number 1. Any questions so far? Is it clear?
No, sir.
It's very easy, I think, question number 1. But Wang only did a mistake in terms of combining Z1 and Z2 because he considered that one as series connected connection in this ZTH value. Anyway, we proceed with the second question. The second question is about, what's the question? Okay, here. It's about another circuit, right? And we have two parts. First part is to construct Norton equivalent circuit at terminal A and B. And the second part is using that Norton equivalent, construct a Thevenin equivalent circuit. Okay, and you need to show all your calculation. And the whole thing is about 14 marks over here. And I will speed up the explanation about the solution. Basically, this is also a very famous question where we have bridge connected circuit. And if you look at example that I gave to you last Tuesday, we have a voltage source over here. In this question, we have current source. Just the difference between those two is just the voltage or the sources that given in the question. However, the way we calculate the solution is almost this. It's about the same. All right. Now, in order to construct a Norton equivalent circuit or Norton circuit, and we know that for Norton we need to find what is the Zn and also what is the value of In. In current flowing through this circuit. This thing. Right? It's In is over here. We need to calculate what is the current here. And later on, draw the parallel connected of In and our Zn. Okay, we proceed with the solution. For Norton equivalent circuit, for Zn, the first one, if you look at the question, we have current source, and in order for us to calculate the impedance, we need to treat all current source equal to 0. And all sources equal to 0. And in this case, we have current source, means that the element over here should be an open circuit element. And the Zn is basically the impedance looking from this direction. And if you draw this circuit, I will give you marks. And if you simplify, it will make your calculation a lot more easier. And I think I've already, or before this, I've explained to you how to solve this, or not to solve, to simplify in order to make your circuit looks more easy to analyze. So here I also apply the same rule, and basically I have two terminal over here, terminal A and terminal B. So from terminal A, I have connection of 6 and this 40 ohm resistor connected in series, and later on get back to point B. So here I have, can is 60, 40. Okay, this is 60, this is 40 ohm. And the other branch is coming from this negative J80 in series with this negative J30. So the another branch is here. And yeah, capacitor over here. Maybe you can also draw like a box element. Ooh, it's very difficult here. Anyway, try to redraw it back. Here, this is J80. This is negative J30. These two element is connected in series, but it is in parallel with the other branch, which is 60 and 40 ohm resistor. So you need to analyze, or you need to have a very clear picture of what happened or what is the connection in order to give us the value of our Norton impedance. So here Norton impedance is coming from this kind of circuit arrangement, and this is the value of our Zn. This you will entitle to get another 2 marks. Solving for IN. So here I use mesh analysis because I think this is the easiest way to calculate this IN, this current. So I redraw back my circuit, include my power, current source over here, and put IN as a short circuit element over here that I would like to really, I would like to calculate what is the value of current flowing through these two terminals, A and B. So using mesh analysis, I define my mesh. Here is I1, I2, and also I3 over here. And looking at the solution, here, okay, if I try to define my current like in this direction, so means that I would first allocate or identify my polarity, voltage drop. So in mesh number 1, this is the polarity. Since the current is flowing this way, means that I also have this polarity. And for I2, since the current is flowing in this direction, means that this is a positive, negative. Again, for this 60, this is positive and negative. And for the third mesh, this should be a positive, negative, and flowing this way, this should be positive and negative. So using this definition, polarity definition, I try to set up my mesh current using mesh analysis. For mesh number 1, it's quite straightforward because we have a current source flowing through this mesh number 1. So I just write down I1 equals to 3 with the angle of 30 degrees as my, 60 degrees as my I1. And you should get 1 mark for writing this one. And for mesh I2, the mesh I2 or the second mesh, I would like, I have to set up the Kirchhoff voltage law around this loop. I have 2 elements over here, and the current flowing through here is considered as I2. However, the current here is not I2 anymore. It's maybe I label this one as IY. So here, I2 times 40, because this is 40 for voltage drop at the first element, plus, okay, this is basically, this is IY that I mentioned earlier. So IY is the current over here, and the current I'm labeled it as I prime. So I prime is coming from this node. So I try to assess this node because I know that this is definite I1. This is a definite I2. So I just want to know what is the current in that direction at this branch. So looking at the simplified or the connection of the current, I can tell that the current that I labeled as IY just now is I2 minus I1. And from here, I can substitute back my I1 because I know already what is I1 and straightforward get my I2 value. And in this, that's settled for mesh number 2. And since the calculation is a lot involved many definition and also try to work out the equation. So here you are entitled to get another 2 marks. And for mesh, the third mesh, again, the third mesh is I3, and I know the current flowing through here is a definite I3 because this is the current from the outside, and the current flowing through here is not I3. This is, maybe I label this one as IX. Okay, IX. And to work out the voltage, Kirchhoff voltage law around the loop. So here I have negative J30 times I3. It's referring to this voltage drop across here. And another one plus I3 minus I1. This is basically IX that I labeled just now. So IX, to get what is the value of IX, I prefer to have a look at this point. At this point, I know that I want to find current over here, and I have the definite I3, it's here, and definite I1 is here. So using that connection or relationship between current in and current out, this is the drawing that I bring into a bigger picture. So in here I label it as I double prime, and of course you can also label it as any current that you like. But remember that the current itself is a combination of 2 currents. All right, from here, again, we set up the equation, and we know that I1 already been given as in mesh number 1. So just substitute I1 and you will get what is the value of I3. And the final thing that you need to know, you need to calculate is that your main objective is to find IN. And IN, as far as we are concerned, in mesh number 1, mesh number 2, mesh number 3, we didn't calculate IN yet. And have a look at the direction of IN. If you're looking at the question, if you look at the question, IN is in this direction. So the best way to know what is the value of IN is by assessing or by looking at the junction, where we know that here, the junction over here tells us about this is IN, I that we try to calculate. This is I2. We already found what value of I2, and this is I3. We also had calculated the value of I3. Using this junction and the relationship of current in, current out, you can say that IN is given to I3 minus I2. So if you assess what is I in this case, and it should be equals to I out. This is Kirchhoff current law. So I in is IN plus I2, and I out is basically this I3. So bringing this I2 towards the other side, and you will find IN equals to I3 minus I2. Good. So that's we're done with the calculation of IN and also the calculation of ZN. This is the time where we put all the information that we calculated into a circuit, a graphical representation. So now, for Norton equivalent circuit, as I mentioned earlier, current should be in parallel with our impedance. And impedance that we are focusing in, or that we are talking about, is the value of our Zn, Norton impedance. So just draw this kind of circuit, parallel connected circuit, and put all the informations over here, and you will definitely get your marks. And finally, if you look at the second part of the question, it says that please calculate the Thevenin equivalent circuit. And if you remember yesterday, and not yesterday, on Tuesday, I mentioned that if you have a Norton equivalent circuit, you can easily convert it into a Thevenin equivalent circuit just by using this source transformation theorem. So here is what happened in the solution. I have this Norton equivalent circuit, and I try to convert it into a Thevenin equivalent circuit without calculating the value of ZTH, and as well as the value, maybe later on we should calculate the value of VTH. But not, the VTH is not coming from the original circuit. It's coming from the Norton equivalent circuit over here. So here ZTH as a ZTH value is supposed to be equal to the Zn, or Norton impedance. So the value not changing till 44.27 with the angle of with angle of 63.43 degrees. However, for VTH, we need to use source transformation over here. From current source representation, we convert into a voltage source representation. And voltage source representation means that this is basically a Thevenin equivalent circuit. And we just use this equation where VTH equals to IN times the value of our Norton impedance. And once you get this value, just draw back the equivalent Thevenin equivalent circuit. It's quite straightforward over here, but the quite good, because just by writing this definition as well as using this easy source transformation calculation, you will get 4 marks in total. So far, I think that's for question number 2. This is coming from final exam a few years back. Any question? Can you follow the solution over here? Okay, thank you so much for your response. Right, now we move into our last question, which is question number 3. And okay, we look at the question first. Number 3, all right. Now, in the question says that referring to the circuit in figure 3, construct the Thevenin equivalent circuit as seen from the following terminal. Okay, we have 4 terminals over here, but we consider 2 terminals at a time. So the first part is terminal A and B. It's over here. And maybe we should neglect this terminal first. Okay, and the second part is terminal over here. Maybe we should not considering these two terminal. I mean, we should neglect these two terminal A and B. So the first part, right? The first part here, before we forgot, if you would like to calculate the Thevenin equivalent circuit, means that the calculation should be our main objective is to find ZTH as well as VTH. And looking at the circuit itself, we have two sources. Means that in order for us to calculate ZTH, all sources in the circuit should be treated as zero value. So this is what happened in first part, terminal A and B. This current, this is a current source basically, and we treat it as open circuit. This is our voltage source, and we treat voltage source as a short circuit element. So we should proceed to the solution. Right, to find ZTH, since this is open circuit, means that I can redraw it back. We have, what happened? Oh, okay. Resistor. We have capacitor. We have inductor in series with resistor, and this is a short circuit. So this is where the open circuit located, and this is where the short. So based on this diagram, we can say that maybe I'll try to change another color. Okay, I can say that these two is in parallel, and later on in parallel with these two. So if I redraw, if I put this one to here, maybe you can see that all these three elements are connected in parallel. So that's what happened when we try to calculate ZTH. I have 10 in parallel with negative J20, as well as in parallel with these two elements in series, 10 plus J10. So towards the end, you will get your value of ZTH given by this value. All right, now ZTH is solved. Now we try to calculate what is the value of VTH, and VTH, according to the first part, we would like to find out what is the voltage across terminal A and B. So that is our VTH that we try to find. And I think it is a good idea if we use source transformation in order for us to solve this kind of circuit connection. Maybe you can try other tools or other techniques, but I think using source transformation is the quickest one or the easiest way to solve this kind of problem. Since we have two sources, one is current source, another one is the voltage source over here. What I try to do is I try to convert these two into voltage source into a current source. So this part is basically being converted here to become current source in parallel with element of this 10 plus J10. And since the current source over here in the same direction, I can easily combine the current source. And basically, you also can combine all these elements. Okay. The elements over here, if we look at the circuit, it is in parallel connected, three elements connected in parallel. So now, having said that, the current total, I total, is given by combination of I1 and I2. The Z total over here is given by the parallel connected element. U is the same as you found over here. Okay, and this is by luck basically. The same value over here you see here and here is the same value, unfortunately, but sometimes the value may be a bit slightly not the same because of the circuit connection. Anyway, since we have the Z total, I total, and we can find what is the voltage drop across here, and note that the current over here is 0. So all the current I total is basically the current flowing through this Z total element. So now the voltage or the VTH we are looking at here, basically the voltage across this Z total, and just using basic Ohm's law, we can find our VTH value just by multiplying I total and also Z total. And as usual, since this is a Thevenin equivalent circuit, means that you need to draw this kind of circuit connection. And you should get marks by doing that as well. All right, that is for terminal A and B, and terminal C and D. Okay, looking at the question back, I should, okay, we should consider that this okay, we are focusing on this part, and this part is considered neglected. Okay, looking from this terminal, what you can see is that if you simplify this one, it will become a circuit which is look like this. Okay, let's go one by one. Let's say we have, this is our boundary or our terminal. Okay, from C to D, I have one element, which is my J10. Okay. Right. I have my J10 element because this is from C to direct to D, I have this element. And from C to D, I also have two elements. Okay, these two elements should be connected in parallel. And why I say that? Because from C, I have this first branch and also this second branch. And what happened to this one? This one should be treated as open circuit, right? Because we try to find what is the ZTH. So this is open circuit, means that I have two branches connected in parallel over here. First one, maybe I have a resistor over there, and this one is my capacitor. And from C here, remember C, two branches, and the two branches will be meet again at this point. So at this point, after that point, I have a current voltage source over here, where this voltage source should be treated as a short circuit. So it means that I have a direct connection up until this part. So this at the bottom over here, I would consider another element. Maybe I can draw it here, which is 10 ohm before it goes to my terminal D. So this is my 10 ohm connection. Again, this is, forgot to label it. This is my J20, and this is my 10 ohm, another 10 ohm resistor. Okay, that's how I try to simplify my circuit. Okay, and that's how I come into this kind of circuit arrangement. It doesn't matter whether you put Z10 at the front, Z10 at the end of the circuit, because both are the same, both are connected in parallel. So here I have my ZTH equals to Z1, where Z1 is a combination of these three elements. These three elements is combined by the first one is in parallel and in series with this 10 ohm. So that's why you see here 10 in parallel with negative J20 plus 10. This is my Z1. And later on, Z1 should be in parallel again in with J10. So at the end, you will have your ZTH value over here. Just by doing this, we easily got 3 marks over here. And if your answer is wrong, maybe I would like to have a look at your drawing. Maybe your drawing is correct. You have some careless mistake over here. I will consider the answer because I know that you understand what's going on in the circuit, or you able to analyze the circuit correctly, except that you did some careless mistake in your calculation. All right, that's for your ZTH. And for your VTH, again, for VTH, we need to consider that we have like the voltage that we are trying to calculate. It's basically voltage across here. Okay. Maybe we look back at our solution. Right, here. Voltage is over here, but I think it's not a good idea if you look back at the ZTH circuit, because it's quite confusing, because of we already removed our current source and also voltage source. Just get back into based on the question, we have VTH over here across C and D, and we would like to calculate what is the voltage across here. And the I think in my experience, I think the best way to calculate this one is by using a combined tool. The first one, I try to make this one as a voltage in series with source, and is with voltage source, and later on I will try to use voltage Kirchhoff voltage law in order to get what is the voltage drop across this element. And maybe if you look at the question earlier, okay, if you look, these two is connected in parallel. So you need to combine these two first. So in other words, I would like to say that the circuit itself, okay, I have a combination of elements over here, and this is my current source. Okay, this is combination. Maybe I put it this one as Z1 in my solution, because if you look from this point up until this point, these two are connected in parallel and in parallel with a current source, so that since we have that kind of arrangement, it is there is an opportunity for us to convert from parallel connected into series connected elements. So here, after the conversion, I would have V1 and Z1 connected in series. Remember that Z1 is a combination of two elements, this 10 ohm resistor as well as this negative J20 XC, and both are connected in parallel. So here I skip all the calculation. Basically, you should use like this: 10 times negative J20 divided by 10 plus minus J20, and try to put in your calculator. Suppose you have got this value. And for V1, we take this value Z1 and multiply it with the value of the current, we will get the value of V1 as stated here. And to analyze what is the voltage across this part, okay, as I mentioned earlier, I use several techniques. The first one is source transformation. The second one, I use superposition. If you look here, not superposition. Yeah. Let's see. Oh, not superposition, because I combine these two together. All right. You can also use superposition in this case, because we have two sources, but I think superposition is a bit longer to solve this one. And we can find a better way to do that by just combining these two sources. To combine these two sources, please be particular with the polarity of the source over here. Okay, if you combine these two, you can say that this two is in an opposite direction. So that's why here I have negative J8 minus J20. This is coming from V1. This is coming from V2. Because both are in opposite direction. V2 is 20 with the angle of 0, so this is my V2, and V1 is 16 minus J18. Why I put this way? Because I would use summation and also subtraction in my calculation, so it is preferable that you use this rectangular form. So that's why I wrote here as in rectangular form. But if you write it in polar form also can, doesn't matter. It's just a matter of how do you process your calculation. And if you look at the combination, the main thing is that the both polarity is in opposite direction. For example, if you have like positive over here, and if you combine this down here, it will become like this. Okay, this is your voltage source, first voltage source, second voltage. So it is in opposite direction. If this source is in this kind of polarity, means that you can simply add them together. So in this case, it is in opposite direction, means that we need to subtract V1 and V2. If you subtract V2 minus V1 also can, because at the end you will get the same answer as you see over here. All right, since we simplify our circuit and combine the voltage to be represented in one value, so using this circuit, there are two ways to calculate the voltage across here. One is by using voltage divider rule. The other one is by finding the current over here, finding the current, and later on multiply it with J10. And in my solution, I use voltage divider rule to do that. And I think this is the fastest way to get my VTH. And once I get my VTH, as usual, at the end, I will try to come up with the Thevenin equivalent circuit to finalize my answer. So that's for the question in solution for question number 3. All right, any problem or any questions so far? Any question? By the way, Wang, thank you so much for your sharing. I think it's you can see your weakness, and you can see how can you gain mark from the solution. Okay, any question?
No, sir.
No, sir. Is it clear so far?
Yes.
Yes, so far so good.
So far so good. I will put this solution in e-learning later on. Maybe I put the one with the annotated version so that you can see the how what are the ways that you can use in order to. This is not the only your answer. Maybe you can try to use other methods or other tools to calculate um, the answers. Okay, as usual, can you turn on your webcam? Okay, according to my record over here, we have around 17 people, including me. Means that one of your colleague is absent today. I think Ame Akil is absent. I've tried to contact him, but he didn't respond. Anyway, you can always find the solution as well as the information about the class later on in e-learning. And again, thank you so much for sharing, and special thanks to Wang as well to share his answer here. And don't forget that I said earlier, you need to go through or conduct the EPP survey. I think Omar Well has a problem for that. Maybe later on we can communicate in the background how to solve your problem. So for the rest, should be no problem for you guys to evaluate me in conducting this class. All right. Thank you for your attention. I think I would like to end the session now. And again, we try to meet again next week.
Tuesday.
Yeah. What is this? TBH is a bit confusing, but everything should be all right after going through it. To be honest. Millennial. All right. Anyway, um, we meet again on Tuesday. Don't forget to evaluate me in EPP. Stay safe, everyone, and hope to see you again. All right. Thank you so much for your attention. Assalamualaikum. Bye.
Have a good day, sir.
Waalaikumsalam, sir.
Thank you, Doctor.
Take care.
Welcome.
Waalaikumsalam, Doctor.
Thank you, Doctor. Seketika itu